Hi, everyone. Thank you so much for joining us today for the PCI Express Technology for Automotive Functional Safety webinar. We'll get started in just a few moments here. Thank you. Hi, everyone. Thank you again for joining us for PCI Express Technology for Automotive Functional Safety as part of the PCI SIG Automotive webinar series. I wanted to take a moment here to introduce you to our speakers. So we have Ron DiGiuseppe, who is an Automotive IP Segment Manager at Synopsys, Stephanie Friedrich, who is a Systems Engineer at Intel, and then Terry Beaumont, who is a Functional Safety Engineer at Intel as well. I'll go ahead and pass it off to the presenters now.
Thanks, Megan. Hello, everyone. This is Ron DiGiuseppe from Synopsys. As Megan mentioned, we are here today from the PCI SIG with Synopsys and Intel to present this webinar on automotive functional safety using PCI Express technology. This is the agenda we're going to go through, and I'll be starting with a quick overview introduction of PCI Express technology in automotive. As Megan mentioned, this is a pair of webinars for automotive focusing on PCI Express. So if you haven't gone to see the general overview webinar that the PCI SIG presented in April, I strongly recommend you take some time and go review that earlier webinar that's on the PCI SIG webinar page back in April, as these two webinars are kind of a pair. So in today's agenda, as you see, we'll go through that overview, and then I will hand it off to my Intel colleagues, Thierry and Stephanie, to talk about some background on functional safety in general, and then specifically talking about the capabilities of the PCI Express specification that is very beneficial for functional safety. And then I will talk a little bit about some additional hardware safety mechanisms that most industry providers add to the PCI Express implementation to meet those ASIL B functional safety levels metrics. And then we'll close with a short summary. So let's get started. As I said, this is a second of a series of webinars that the PCI SIG is putting on for automotive. And this webinar, we'll talk primarily about PCI Express, but we should kind of remember the different applications in automotive that PCI Express is widely used. So I'm just showing a couple block diagram use cases that PCI Express is very popular in automotive. First use case, as an example, is using PCI Express in an ADAS domain controller. You can see a typical domain controller would comprise of some sort of a host, processor, SoC, and very typical with the amount of AI that is in automotive applications. It's very typical to have separate AI or co-processing accelerator SoCs, accelerator chips. So you can see this block diagram, an AI accelerator, for example, performing some deep neural network machine learning or co-processing, heterogeneous system. and then using a PCI Express switch to connect to storage or additional accelerators. So in all these chip-to-chip implementation, PCI Express is critical, mission critical for this type of application. You can see some of the technology requirements that the application requires, and PCI Express is ideal to meet those technology requirements, such as a high bandwidth and to be able to scale the performance based on the number of lanes or the PCI Express generation, which has higher data bandwidths, very low latency, because it's a heterogeneous implementation. Virtualized hypervisors are required, and PCI Express has specific capabilities to lower power, works very well with new security capabilities. And of course, since we're talking about functional safety applications in automotive, functional safety for such a PCI Express based domain controller is absolutely critical. Then when we look at maybe another application, such as the new zonal architecture that is starting to be designed for next generation automotive in-car networks, we can see the distribution of many sensors and different gateways in this zonal architecture and a central processing module. It's very possible to use PCI Express as a data backbone. In this use model, it's more of a long reach, so very close attention must be paid for EMC and EMI, electromagnetic interference. But the capabilities that PCI Express brings in terms of high bandwidth and very low latency and the new security capabilities, plus, of course, functional safety is ideal for such a new zonal architecture using PCI Express. Then when we look at maybe a couple other applications, you probably know that SSD for storage in automotive is the new requirement for, especially for things like automated driving, autonomous vehicles. They will use lots of SSD capabilities, and we can see that PCI Express, with its very high bandwidth and fast boot startup time, very low latency, the ability to work with SSDs that have very high endurance and data retention, the ability to manage power and therefore keep the temperature of the implementation low, and having virtualized SR-IOV, all make PCI Express for use in automotive storage very beneficial. And of course, these applications will require functional safety. And then just another use model where the automotive TCU, the telematics control unit, where you might have the new 5G modems, V2X applications. Of course, there's in-cabin Wi-Fi and Bluetooth. These TCU applications can also benefit by the high bandwidth and throughput that PCI Express provides, the PCI Express specification, the features in the spec that use very high data reliability and integrity. And as we already talked about, electromagnetic interference is minimized by using PCI Express. With also security, and as I mentioned, there's that trend, functional safety in all of these applications. So functional safety is very critical for automotive in general, and this table shows those four different use models, whether it's chip-to-chip, long reach, chip-to-module, and the various applications I was talking about, whether it be ADAS or in-vehicle infotainment, autonomous vehicles, zonal architecture, black box storage. And so we come to looking at a leading edge high performance SoC for automotive, and here's like an example of an ADAS SoC where PCI Express is mission critical for the whole implementation of the SoC as well as the implementation of the automotive module, the ECU. Such an SoC would be multi-processor, could be as many 12 processors using external DDR and very high performance connectivity. Could have some sort of a DSP, depending if it's radar or LiDAR or embedded vision, AI applications. And of course, since it is automotive applications that may require functional safety, which is what we're here to talk about today, we see functional safety is required to implement these mission critical applications that PCI Express can provide for automotive. So with that background, I'm going to be handing it off to my colleagues, both Thierry and Stephanie, to provide more information that the PCI Express spec, as well as the compliance to functional safety, which is required. So here's the next presenters to talk about some of the FUSA background.
Hello, so thank you, Ron, for this introduction. So my name is Thierry Baumann from Intel, and I'm here to give you some background on functional safety. So I'll go as fast as possible towards going back to the example that was used by Ron. But first, I'd like to show you a little bit of what are the functional safety standards. And I will go through two definitions before going to this example, which will be ADAS and lane departure warning. So, like you can see, the functional safety standard, they have their sector of application. So you have the industry, you have the automotive, but you have also railway, you have medical, you have nuclear power plants, you have furnace. Each sector really has its own application standard because it has its own specific use and risk. So the one I want to show you first is 61508. This is a foundational standard. It's is definitely used in the industry, but because it's a standalone, it's also the base for sector-specific standards such as the automotive industry. And the one that is governing the automotive industry is so-called ISO 26262. It's a second edition that was released in 2018. The first release was in 2011. And it addresses passenger vehicle, mainly. Now the extension address also trucks and the motorcycle. And what you will need to keep in mind here, or like I would like to highlight, is the goal is to address the malfunction of that system in the presence of a fault. So we're not talking about a system that is need to have some operating design domain, that's another standard, but more, okay, the system has been developed and now it is released into production, into the general market, and now there is a fault, and how is the system going to behave? The system is very big. It's got 10 parts. Sorry, there's 12 parts, 10 that are normative and 2 that are guideline. So the two definitions I want you to look at with me are mentioned in the part 1 of the standard. So the part 1 of the standard is all about vocabulary. There is more than 300 definitions. And the reason I choose those two is because it depicts what are those faults that the standard wants to address. So a fault, for definition, is an abnormal condition that can cause an element or an item to fail. We'll talk later about position of element and item. So the really important part is, those faults, they can be permanent fault, they can be transient fault, and they can be systematic fault. So permanent fault is, those faults happen and they remain. Stockats are an example of it. The transient faults are more related to something that is happening and then is disappearing. A bit flip, for example, will be an example of a transient fault. And we need to pay attention to all of those three types of faults because they all contribute to the safety of the system that we want to release into the market. How is the ISO 262 going to address those faults is by guiding the development of safety measures. And I choose the term safety measures to the opposition, or let's say opposition opposite will be in that case a safety mechanism is because safety measure does not necessarily address something that do a detection or control a system, but more an activity. So when you develop according to a process, when you make review, those are activities that you perform, and they all help into avoiding, controlling systematic fault. They all participate to the detection of hardware random failure, control random hardware failure, for example, ECC or parity, and mitigate their harmful effect. If you are able to detect a fault, you are able to report it. You are able to warn the user that something won't happen. So, Ron presented this ADAS system. So the ADAS, let's take an assumption that we are using now the lane departure warning. So the lane departure warning is a functionality of this ADAS, and it's going to be very important through the part 3 to conduct hazard risk analysis and risk assessment. So this is a so-called ARA, and that ARA is going to allow you to define what is the risk that is exposed and the automotive safety integrity level, so the so-called ASIL. So when you conduct your analysis on your item, you will find all of those hazards, and then you will have a table that will allow you to establish the exposure, the controllability, and the severity. And this is going to give you this ASIL level. The combination in this case, so E3 plus C3 plus S2, give us an ASIL B. Now, because you see there is all of those functions, all of those, well, let's say there are several functions, several elements that are participating to those functions, then PCI is one of them. And in order for the system to be viable, I would say, you can develop according to ISO 2626 part 10 clause 10, which is a safety element out of context. It's an important notion because it allows you to develop something that is not for a specific item. What you do for a lane departure warning can be applied to another functionality. So that's an important dimension of the standard that is very useful. The standard is big, like I say, so I'm going to be zooming here in 4 main parts. So the part 3 that we saw earlier defines this item. It will provide you functional safety concepts, it will initiate the safety plan, and then you will be feeding to the system development, which is this part 4, and the hardware, which is a part 5, and the software, which is a part 6. What this slide shows you with this work product is that every time you conduct a requirement in which is expected by ISO 26262, the result is this work product. Each of those elements bullet that I listed here are either part of the left branch of the V development phase or the right branch, which is more the validation, the verification, all of those activities that you put in place to verify that what you have developed is actually matching your expectation. And I conclude here with this bullet, which is a safety manual, because that safety manual is really a strong element to understand how your product is going to be reusable. So you're going to give this to your user so that they integrate your product accurately without misunderstanding some things that you have assumed on your system. So ISO 26262 is a very requirement-oriented product, a standard. So the purpose is to really capture the systematic fault. Systematic fault are something that can only be eliminated by a change of a design or in a manufacturing process, because you know that you have too much exposure to some radiation. The electromagnetic element that was also mentioned by Ron. So the work products that are participating just for the reduction of the systematic fault is all of those that are listed here. But what I want to show you also is it goes all the way to which are the tools that you are going to be using in order to do this development. So if you are doing unit testing with a tool, you will want to make sure that this tool is actually doing its job as expected. And you will want to classify, making sure that it is not going to be violating your expectation. The other aspect that the ISO 26262 will address is those hardware random faults. So hardware random faults are everything that can happen on the hardware level that will create a stuck at bit, an over voltage condition, but also those soft error that are due to radiation strike. So the transient faults are modeled according to GDS specification, which aligns the industry on how do we model those testing and how do we verify the radiation. And it's very useful for ISO 26262 when we do this random analysis, because we take this as an input in order to conduct the next step on how do we mitigate those transient faults. The permanent faults are something that you need to consider also, because if something happened and then in conjunction with another fault, you actually violate your safety goal, you will want to detect this. And this is how those two metrics are appearing according to the criticality of your system. You have the single point fault, which is this fault alone will violate your safety goal. And you have the latent fault, which is a fault in conjunction with another fault is going to violate your safety goal. So you will want to make sure that when you want your safety mechanism to be used, it is actually functional. So that's a latent fault matrix. Your ECC mechanism is used in order to mitigate transient fault. You want to make sure that it's working prior to using it. So with this, I will pass on to my colleague Stephanie for the information related to the specification of the PCI SIG.
All right, thank you, Terry, for the general introduction to functional safety. The PCIe architecture provides a rich set of error detection, reporting, and logging capabilities, which build the basis to enable functional safety. And within the next slide, I will introduce the PCI Express specific features and point out the safety expectations on one PCIe use case. So when we look at the automotive applications, we see a trend to increase compute capabilities, as well as an increasing demand of high bandwidth and low latency connectivity, as also Ron gave an introduction at the beginning. The picture on the right shows an example of a high-level block diagram of a modern automotive multi-SoC platform. In this system, PCI Express is used in various ways, virtualized as the white lines between the boxes. So for example, we have chip-to-chip communication between the SoCs in order to provide compute scalability by sharing information between processing elements through PCI Express. In addition to the communication between the processing elements, PCI Express is also used to connect, for example, accelerators for machine learning or computer vision, and to connect mass storage devices to the main processing unit. The PCI Express connection can be directly between two devices, or it can also be routed through PCI Express switches. PCI Express already provides the requirements for scalability, high bandwidth, and low latency, and improves these features in each new generation. Applying such multi-SoC platforms for automotive requires the system to meet also the demands of the functional safety ISO 26262 standard. However, the PCIe spec has not been developed according to this ISO standard, but already provides the basic requirements for functional safety inherently. So in the following, I will show more details how PCI Express is implementing mechanism to protect and mitigate faults which might lead to an unsafe state, and how we can prevent these faults become hazardous. So when we look at the PCI Express architecture, we see a 3-layered architecture for communication between two devices. The data link layer is responsible for packet error and response handling, and to make sure that every transaction layer package called TLP arrives to its destination correctly. It includes a link cyclic redundancy code, the LCRC, that protects the content of a TLP across a single PCI Express link. An acknowledge retransmit mechanism makes sure that no TLPs are lost on its way. A flow control mechanism makes sure a packet is sent only when the link partner is ready to receive it. All in all, whenever a TLP is handed over to the data link layer for transmission, we can rely on its arrival, even if there is a slight uncertainty regarding the time of the arrival. Failing to deliver a TLP is then a major malfunction of the bus. Even so, the data link layer gets a positive acknowledge that only means that the packet made its way safely to the nearby switch. No end-to-end acknowledgement is ever made, and neither it is necessary. In the example on the previous slide, I showed that we not just have direct connections between two devices, but there are also connections throughout switches. Since the LCRC is regenerated by PCIe switches, it increases the risk of data corruption. In order to secure end-to-end data integrity, a second cyclic redundancy code is added in the upper layer where packets are formed. This CRC code is called eCRC. The transaction layer checks are done at end-to-end and are not performed at switches or bridges in between the requester and the completer. The eCRC failure checks are an optional check based on eCRC and the advanced error reporting selection. If data is corrupted, the packet will be reported as a poisoned packet. With these methods, we can ensure that data is transmitted reliable from the requester to the completer, and errors are reported by enabling the optional advanced error reporting feature, which will be described in more detail on the following slide. When we look So the PCI Express defines two error reporting paradigms, the baseline capabilities and the advanced error reporting capability, which are shown on this page here. The baseline capability is required by all PCI components, providing a minimum defined set of error reporting, such as single data parity errors. PCI Express advanced error reporting, extended capability structure, provides a more robust error reporting and control. The AER registers are mapped into the extended configuration space and provide much more information about the nature of an error for diagnosing and recovering. Since AER is only one capability of a large list of PCI Express extended capabilities, it's defined by the header shown in the lower left picture. The advanced error reporting extended capability structure is shown in the picture on the right side. The error registers show the status of individual errors on a PCI Express device function and define the error severity, the error logging, the error mask ability, and are used to identify the source of an error. Based on the severity of errors, PCI Express errors are categorized as the following. So first, we have correctable errors, which can be recovered by hardware without the intervention of software. This may have an impact on performance, but no data or information is lost, and the PCIe fabric remains reliable. The second categorized errors are uncorrectable errors, which are classified as fatal and non-fatal errors. So uncorrectable non-fatal errors are handled by device-specific software, while uncorrectable fatal errors are handled by software. With the ability to detect failures reporting, the failures are reported to the system software and then proceeds to a safe state. So this means that AER supports the general safety goal of a system. So when we now look back at coming back to the example, which I showed at the beginning, the safety goal of the system is not specifically defined for PCI Express only. It is the goal for the complete system to be safe. So we have a top-down hierarchical decomposition is conducted to assure appropriate safety measures are put in place for each functional block within the system. So an example of a safety goal for a system can be the following for automotive designs. The vehicle keeps distance to road obstacles. And then an example of a definition of a safe state would be the automated driving function gets disabled and the driver gets warned. So as shown before, PCI Express provides data reliability in order to guarantee that there is no corruption in the data transfer. For example, by retransmitting packages when ECRC or LCRC are indicating issues and detecting and logging errors to mitigate harmful effects of malfunctional data transfers. The picture on the lower right side draws the error logging and handling of a typical SoC. In the error detection process, errors are discovered by an agent as a result of a local problem. In the next step, the appropriate bit is set in the AER register, which I showed on the slide before. And then based on this detected error, it's also logged. This logging bit is later used by the error handling software. In the last step, the system is notified of the existence of the error condition, for example, by delivering an error message to the root complex in the SoC. The root complex in turn then sends an interrupt to the system when it receives an error message. The completion status field is used by the completer to signal an error to the requester. Both the requester and the completer can be either a root complex or an endpoint of the PCI devices. Examples for completion errors messages are, for example, unsupported requests, completer abort, or poison TLPs. And with this, I'm handing over to Ron, who will focus now in the next section on additional safety mechanisms to meet AC levels and beyond.
Thank you, Stephanie. This is Ron once again from Synopsys. And theory talked about the ISO 26262 standard and what are the primary features that need to be implemented in a functional safety critical system. And Stephanie very appropriately showed the current capabilities of the PCI Express specification that includes features such as LCRC, ECRC, the AER capability that are absolutely required to meet the safety level, and PCI Express offers that capability. But depending on the target safety level, we see many industry implementations add additional safety mechanisms beyond what is already contained in the PCI Express specification. And this block diagram, which shows PCI Express layers, the physical layer, data link, transaction layers of a PCI Express implementation, show some additional safety mechanisms that industry leaders add to their PCI Express endpoint to make sure they hit those ASIL levels, and in this case, ASIL B. So let's take a look at some of those additional safety mechanisms that can be added, and it's based on each design implementation, the design team working with the functional safety managers would jointly decide are necessary to add to the endpoint to meet that target ASIL level. So we can see, going kind of clockwise from the left-hand side, it's very common to add ECC for all of the SRAMs used in that PCI Express endpoint, whether it be for some sort of buffer memory or FIFO or just small storage SRAM. All SRAM should have ECC, and that's probably a good idea for all the SRAMs in the chip, in the SoC, is to add ECC for that. But in addition, there's some additional safety mechanisms that many industry leaders add. And if you take a look at the data path that goes through the physical layer up through the transaction layer, it's very common to add safety mechanisms like parity protection for that internal data path. And Then when you look at the user interface, that is the interface between the transaction layer and whatever, on-chip fabric that may be used in an SoC. It's typical to connect the PCI Express endpoint to a NOC, on-chip NOC, and taking a look at the user interface between the PCI Express endpoint and that NOC, you can see that many industry leaders add parity protection for that user interface. And then when you kind of look at that user interface in a little bit more detail, it's probably a good idea when you select an on-chip fabric, a NOC, to have the interface between the PCI Express endpoint and the NOC to use the same safety mechanisms. So one approach would be to add ECC to the data path ports of that user interface. And of course, there's address ports. Might be a good idea to add parity protection to the address ports. One of the point I'm making here is it'd be easier for the design to select a NOC and the PCI Express implementation that uses the same user interface safety mechanisms. So if it's ECC on the data path and parity on the address ports, it'd be nice that the NOC matches that implementation, or it could be backwards. Parity on the data path and ECC on the address ports, but more typically what we see is there. And then, of course, the PCI Express endpoint has a register space. We really need to protect those configuration registers. The last thing we want is some sort of a fault which causes a failure in the PCI Express endpoint to be developed in the configuration registers of the register space. So very important to protect that register space, and the implementation can be in multiple ways. It could be in order of TMR, triple mode redundancy, or duplication, or additional parity protection. But last, it's very critical to protect the configuration registers. It will determine the PCI Express endpoint is in transmit or receive mode, and that's where you certainly want to protect those configuration registers, the register space. And as Thierry mentioned, you have to add safety mechanisms that will detect and correct both permanent and transient faults. And when you design those safety mechanisms, you have to take into account the reaction time if there is a fault that would lead to a failure. Your design must implement some sort of error flag handling and monitor the reaction time of the register which flags the error, and the application layer that would have to react to that possible fault that occurs. And so with that in mind, it's also important to perform various built-in self-tests, specifically logic built-in self-test, to make sure your PCI Express and the rest of the SoC has managed the functional safety. So this block diagram shows a PCI Express endpoint on the bottom right-hand corner interacting with the rest of the various blocks of a typical high-end processor-based design, such as an ADAS controller. You'll see multiple applications processors, maybe DSP processors, various AI compute accelerators, memories, and interfaces in PCI Express. It's fairly typical to have an independent safety manager managing the functional safety, which offloads your applications processor to run up applications. So having a separate independent safety manager processor monitoring and managing the safety escalations, managing the BIST activities is a very typical design function that leading edge automotive SoCs will typically use for safety critical designs. For those safety critical designs, we want to make sure that there is a safe boot And there is a LBIST safety test that occurs during boot. But in addition, it's very typical to meet ISO 26262 requirements to have a periodic testing where it exits mission mode to a periodic test BIST mode, and having a LBIST infrastructure that could put all the various blocks, including PCI Express, into a BIST test mode and perform a periodic BIST self-test to ensure the functional safety is running properly, is what most of the industry leaders are implementing in their latest safety critical designs. And the management of the safety management of the BIST with some sort of integrated BIST scheme that puts it in a BIST mode and isolates the various functional blocks and isolates the PCI Express endpoint with a wrapper, allows that BIST to occur not just at boot, but periodically during mission mode to do that periodic safety test. So it's very critical that your PCI Express implementation works seamlessly in that LBIST mode. Then when we look at that PCI Express endpoint and how the endpoint engages with the system, with the application, if there happens to be a fault that occurs, and that fault could possibly lead to a failure, the PCI Express application should monitor the safety interrupt outputs from that PCI Express endpoint. So when you design the PCI Express endpoint in the SoC, you have to implement a design scheme where if there is a failure, the application transitions into a safe state. And Stephanie mentioned that the possible safe states that users do for like that lane departure warning application. And if there's a potential failure, the PCI Express application needs to respond to those potential failures. So as the theory said, you have safety goals, and if there is a failure that violates the safety goals, the system has to respond to that. So we have the various safety mechanisms that Stephanie and myself described, and if a failure happens, the system has to respond to those failures. And so when you design your SoC, you want to plan how your PCI Express function would respond to those possible failures, both in permanent hardware faults. A response may be to perform a reset, or a transient based failure, in which case maybe the response to a failure is replay the PCI Express data with data correction. So based on each of the safety goals, based on each of the implementation of the safety mechanisms, you really have to look ahead and not just prevent failures. You need to plan how your system will respond to a failure if it does happen. And the different implementations of PCI Express, the different safety mechanisms available in the PCI Express spec, gives you the capability to enable that response. So with that, we talked about the usage of PCI Express in safety critical automotive applications and some of the capabilities that the PCI Express specification contributes to that implementation. We talked about the background of the ISO 26262 functional safety standard that the automotive supply chain, the OEMs, the tier 1s, the tier 2 SoC developers, and the IP providers to those tier 2s need to meet for the automotive safety critical applications. And you have to design your SoC with PCI Express to identify and correct possible faults that could lead to failures, both permanent and transient faults. You have to develop your implementation using specific functional safety development flows that meet the ISO 26262 ASIL systematic level that you're targeting. And really, since PCI Express is mission critical for those applications in many of the different use models, whether it be chip-to-chip or a long reach or chip-to-module, we see that PCI Express is required, it's mission critical for those automotive SoCs, especially in those safety critical applications. So we really appreciate you joining this webinar, and we see that there's quite a few questions that our listeners have submitted. And what I'd like to do now is pass it back to Megan, and she could highlight some of the questions that we see. And Megan, so what would you think would be the first question from our audience?
Thanks, Ron, Stephanie, and Thierry. First question here, to achieve ASIL D FUSA safety level, which additional safety mechanism are needed to add to the PCIe endpoint?
Well, I think I can take that question. This is Ron from Synopsys again. So as Thierry mentioned in the ISO 26262 standard, there are different ASIL safety levels, and a developer, a designer team should perform a HARA analysis to determine which safety level your product needs to comply to, and you really should look downstream to your potential customer. What is the customer's safety level they will be requiring? So after you perform that HARA analysis, if you determine ASIL D is required, Thierry also mentioned that ASIL D requires a FUSA ASIL metric of 99% detection of single point faults and greater than a 90% detection of possible latent faults. So you perform your HARA analysis, you implement according to the development flows that Thierry showed earlier. You got to see what are those additional safety mechanisms that may be required to hit that ASIL D level. A lot of times ASIL B is adequate for different systems, but if you design the ASIL D, some of the possible safety mechanisms that can be done would be to add some additional parity protection, for example, into some of the lookup table entries in the PCI Express endpoint, maybe add some additional duplication or triplication, that's TMR, triple mode redundancy, to some of those critical finite state machines. That's kind of common to increase the result of the ASIL assessment. That ASIL assessment is done in that FMEDA, but create additional TMR in the finite state machines, maybe additional TMR in the various control signals within the PCI Express endpoint, and also possibly looking at the clock domain crossing, protecting those clock domain crossing with additional TMR. So these are just possible safety mechanisms that can be added to increase the resulting safety level from ASIL B to maybe ASIL C or ASIL D, but it's up to the designer to assess what is required in order to implement and hit those higher safety levels. But here's some examples. I hope that answers the question.
When you say end-to-end, are you saying that the PCI switches are doing transport cut-through bridging and are not considered a link point to provide LCRC detection?
Yeah, so I can take this question. So first we need to differentiate between, because we have two of these cyclic redundancy checks. So we have the LCRC and the ECRC, and the end-to-end check is the ECRC. So LCRC is used to detect errors in TLP packets on a link-by-link basis and applies also link-by-link retransmit mechanisms for error recovery. And so as a transaction layer package passes through a switch, the PCIe switch may need to change some control fields without modifying other fields that should not change as the packet transfers the path. So for example, the data inside the packet should not change. Therefore, the LCRC is regenerated by the switch, and this might then corrupt the data internally in the switch because there are some failures in the regeneration. And then in order to, and this is only applying to the LCRC, and in order then to secure the end-to-end data integrity detection in the system, we require high data reliability. So this is why we are adding in at the end of the transaction layer package another CRC code, and this is the eCRC. This is not taken into account by the PCIe switch in general, so it can be applied as well. But basically, this is only to secure the end-to-end data reliability. And yeah.
Thanks, Stephanie. Is the LCRC based on the entire physical connection, or is it lane dependent?
Yeah, so I can also answer that one. So it's not lane dependent, and also because it's above the physical layer. So I showed before that we have these 3 layers, and at the end we have the physical layer, and the LCRC as well as the eCRC checks are not dependent on the lanes. So it's the physical connection which is taken into account.
Next question here, since the system integrator will need to get the system certified for all elements, how do you handle the certification when considering that PCIe was not designed for the following safety process?
Yeah, thank you, Megan. So I'm going to take this question. So it's not because a stampede is flop according to functional safety that it's not suitable. Again, I think I want to leverage also what we exchange about is it depends. What does your analysis demonstrate? Is your product really not suitable at all, or does it still have some capabilities that you can leverage? So I think in this case, I will recommend to apply ISO 26262 and see where are the elements that you comply to it and where are the elements where you do not comply, and are they potential mitigation. Discuss, exchange with the suppliers. This is one of the mission of ISO 26262 is to establish requirements between suppliers. So at your product alone, you might look at it and say it's not suitable. But when you place it into a complete item, which is really the functionality at the vehicle level, maybe other elements might be useful for mitigating. And then the certification comes into more, an independent person looking at your evidence and demonstrating if they are or not accurate. Have you understood ISO 26262 as it is expected, or did you miss something? So I hope I answer this question and meet the expectation of the person asking.
Can you comment on the software aspect to work with hardware FUSA features that you described?
Yeah, so this is not an easy question to answer, or at least there is no short answer to that question. So where I can comment on is when I showed the AER features, we have on the, let's say, hardware level, we have the transmission. So we need to take about signal integrity so that the signals are actually delivered by hardware. And then when they are kind of received by the root complex in these SoC, so the root complex then we come to the software level. So the root complex then sends an interrupt to the system that it receives an error message. And so this is then more also platform specific. So this is of course not a general PCIe definition. So for example, the recovery process on Linux is after an error is detected and logged, an interrupt that the occurrence of an error happen. And then the interrupt handler performs the recovery of the main API implemented by the device driver. So there we have the interaction between software and hardware, but yeah, of course, there's also, this is a broad topic where you can also talk more about. But yeah, so hope this gives at least a short answer to the question.
And I would like to just add onto Stephanie's response, just to highlight, and I think Thierry mentioned this in his ISO 26262 overview, in that there's a whole chapter in the ISO 26262 standard on software development, how to ensure your software development especially meets the systematic development to prevent possible bugs. So in addition to everything Stephanie mentioned, I highly recommend the reader read that software chapter in the ISO 26262 standard.
Great. Next question here. Can PCIe be used for connections outside of the ECU? If so, what additional features have been implemented to address automotive reliability and safety requirements?
This is a great question, and this is Ron, and I can answer a little bit about it because I showed one of the PCI Express long reach applications for automotive, a possible use of the data backbone in a zonal architecture. To answer the question, most of the features that we have highlighted would be used in that sort of long reach application. The AER and CRC, LCRC functions, as Stephanie mentioned, the data path integrity, such as ECC and parity in the data. And also I want to highlight that reliability is complementary to functional safety. So reliability needs to be implemented in terms of the design to make sure that the product can meet that 15-year operational lifetime, that can meet the low defect densities that automotive applications require, close to zero defects part per million. So the reliability, making sure that it functions correctly, is complementary to the functional safety. And as I said, the safety mechanisms that we've already described would be absolutely used in a long reach application, just like it is in a chip-to-chip application. Any other comments from the team on this one in terms of a long reach connection outside the ECU?
Yeah, I think to complement, I think so. When this feature will be available and it responds to an application in the automotive, there will be a need to integrate it, and the integration for the vehicle will be done by the somehow vehicle manufacturer or someone that is providing the system, then where there is a need of interconnection. So there will be a need of validating some of the assumptions that have been made within the vehicle. Will that have been sufficient before the integration? Normally, the steps of ISO 26262 identified early enough this need and allow to correct or mitigate the fault appropriately of the environment of the automotive industry.
Great. Thank you all so much. So that's actually the last question that we have time for today. We just want to thank you all again for attending the second entry in the PCI SIG Automotive webinar series. The slides will be available to download on the PCI SIG website, and a recording of this webinar will be available both on Bright Talks and on the PCI SIG YouTube channel. Thank you again to our presenters and everyone who attended today.
Yes, thank you.